they also, like the Lagrange polynomials, have a geometric decomposition. By that I mean they're either, so this one is 1 at one endpoint, 0 at the other. This one is 1 at the other endpoint and 0 here. And these are 0 at the endpoints, which means that you can assemble them together just like you would Lagrange polynomials in the standard finite element method. This idea of geometric decomposition, this term was used in a recent paper by Doug Arnold and Rick Falk and Ragnar Winter, where they used geometric decompositions for exterior calculus bases, and the simplest H1 polynomials are the Bernstein polynomials in that case. Okay, now so with that review in hand, let's look at what these look like on a simplex. So it turns out, since I care about arbitrary spatial dimensions, I need some notation that will deal with that. So we'll use multi-index notation. So multi-index is just a tuple of non-negative integers, and its length is the number of entries that it's got. So the order of a multi-index is just the sum of, since they're non-negative, I don't need this absolute value here, but it's just the sum of the entries. Okay? We often use this notation in PDEs. Anders uses it inside of FFC quite a bit. So now I will have AD denote the set of all multi-indices of length D plus 1. Okay? And then within that, I want to have the set of all things of length D plus 1 whose order is n. And I will need these sets of multi-indices to parameterize polynomial bases. Okay. I'll also have, this is the multi-index that is 1 in the component I and 0 in all of the other components. Okay, so like a canonical basis vector from linear algebra. Okay, so some operations that we can do on multi-indices. Some, but not all multi-indices can be compared with a less than operator. So if alpha I is less than beta I for every entry in it, then we can write alpha is less than beta. Okay. You can always define a sum of multi-indices just component-wise. It's just vector addition. We can also define a factorial of multi-indices. So if you have a multi-index, you've got a tuple of non-negative integers, so you can just take the factorial of each component and then multiply them all together. And that's what I mean by the factorial of a multi-index. Okay? And now if alpha is less than beta, you can also define subtraction, just by subtracting everything. And since alpha is less than beta, this is guaranteed to still be a multi-index. Okay? Now, so I know there's at least a couple people who have had to come to terms with scheme in it. So by the way, if you know scheme, everything on this slide is just Kant's car and cutter. Okay, so I have a little bit of notation here that, so if I have a multi-index that's in AD, I'll prepend a member A just by sticking it on the beginning. And I'll use this symbol to denote that. Now I'll also use a prime to say take a multi-index and just take the first term off of it. Okay, and so this is just the cutter, if you will. And then, so an identity is if you have a multi-index, you can break it up into its first term joined with the rest of it. Okay. Now, so in higher dimensions, just like on the line segment, you can define the barycentric coordinates, and it's very rich geometrically. They give you a lot of information. So if you have a simplex with D plus 1 vertices, then you have D plus 1 barycentric coordinates. Each one of them is an affine mapping that they're just the linear Lagrange polynomials. They're 1 at one vertex and 0 at the rest of them. So this would be vertex 1, and so B1 is somehow associated with this vertex. All of the barycentric coordinates, you sum them up to 1. So it turns out they're also called areal coordinates because they represent the ratio of the area of this triangle to the area of the total triangle. So if B1 is 1, that barycentric coordinate is associated with here. So these two triangles would have 0 area, and this triangle here would fill up the whole triangle. Okay? So in order to construct the barycentric polynomials, the Bernstein polynomials on a simplex, you need the multi-index notation and the barycentric coordinates. So I'll just let BD be this tuple. It's got each of the barycentric coordinates in it. And then for any multi-index, you can define B sub D alpha is just take each of the barycentric coordinates, raise it to a power, and multiply them all together. So that looks like a monomial. You saw this in a special case when I did the 1D polynomials. Okay, and then, so if you take, you can take the Bernstein polynomials. So this is all multi-indices of length d that add up to n. And you can just weight n factorial by alpha factorial. It's a generalized binomial coefficient. And you can put this weight in front of the set of all monomials. And those are the those are the Bernstein polynomials on the simplex. Okay, so all of the nice properties that we saw for the 1D case still hold. So they're non-negative, they have unique maxima, they form a partition of unity. You still get some nice approximation theory results, and you also still have a geometric decomposition of them. Okay, so other than not being nodal like Lagrange polynomials are, they can stand in a finite element method anywhere you would use Lagrange polynomials. Now, there is a neat rule. So this is actually the heart of the talk in some ways. That this is going to give me exact formulas for mass matrices that I'll be able to play some neat games with. So it turns out if you have products of barycentric coordinates on a simplex, there's an exact formula for integrating. Okay, so if you take b1 to the alpha 1, b2 to the alpha 2, it just has factorials divided by some factorials here. In the general case, it's a barycentric monomial is the product of all of the powers, and then it's the order plus the spatial dimension. And then you pick up this factor of the spatial dimension factorial times the hypervolume of the simplex. Okay. There's some other algorithms that I'll need for writing things in Bernstein polynomials that will turn out to be important in just a moment. So if you have a polynomial of degree n minus 1, it's a basic fact of algebra. It's also a polynomial of degree n. Okay, so here u I've written as a polynomial of degree n minus 1. It's got some coefficients times the degree n minus 1 Bernstein polynomials. So it's a polynomial of degree n also. So I can write it as a sum of the nth degree Bernstein polynomials here. So there's a mapping c to c tilde. Given the coefficients of degree n minus 1, construct the coefficients of degree n. This is a linear map from from r to to the size of one polynomial to r the size of the next polynomial. And that should be an extra bar there, have a typo. And so this is called degree elevation, and you can represent it as a matrix. Okay. In fact, you can represent it as a very sparse matrix, and that will be really, really important in just a few minutes. So it turns out that if you look at the structure of it, so EDN, by this I mean the operator that works on the D simplex and elevates degree n minus 1 polynomials into degree n polynomials, has d plus 1 non-zero entries per column, and that is independent of the space of the degree of the polynomials. Okay, so if you've done computer graphics, you've seen these kinds of results before. Okay, so just like that, differentiation also has a sparse representation for the Bernstein polynomials, unlike for Lagrange. Okay, so if I have a polynomial of degree n, I'll write it as a sum of my Bernstein polynomials. Its partial derivative in any direction you like is a polynomial of degree n minus 1, and so I'll write it as a linear combination of the degree n minus 1 Bernstein polynomials. So you can introduce a matrix D that acts on the simplex, a degree n particular coordinate direction, that takes C into C hat, and that encodes differentiation. Well, what does that matrix look like? You can go through the chain rule. D by dxi, you can differentiate with respect to the barycentric coordinates, and then differentiate the barycentric coordinates with respect to the coordinate direction. And then if you look at what the derivative of one of the basis functions is with respect to a barycentric coordinate, it's just a monomial. It's either 0 or it's alpha times a lower degree polynomial. So this says actually that the derivative matrix has d plus 1 entries per row at most, no matter what the polynomial degree is. I'll give you examples with specific values of degree elevation and differentiation in a moment. Okay.